the department, from all the members who are present and the participants. It's really privileged that we are having such an training program for such an exposure for the school teachers. And if you look at science, okay, this is basically, I am also a man of science. So if you look at science, science is basically, it is based on demonstration, practical based study. So more we demonstrate, the students are now when the teachers are there, the more you demonstrate in the class, the students will be more benefited. They can understand better, because whenever something visual is definitely better than something only audio or audience. So it's always good to demonstrate, and whatever you are going to learn today from this 5 days 6 days training program, I request all the teachers to develop something so that you can demonstrate to the students. And second point is our basic intention, whether it is Bigyan Academy or Regional Science Center or the state government or even central government, we want to inculcate scientific temper among the students. And that is possible. That is possible if the teachers, particularly the school teachers, who are the truly the torch bearer of science and popularizing science among the students, they come forward. So a positive attitude from the school teacher will take science to a height, and always inculcate a scientific temper in the mind of the student, telling how to analyze very small events that is happening in and around a student, whether it is up to class 6, 7, 8, that these small events, very common events which is happening, how to translate that into a scientific process. He should ask that what is the science behind this. For example, I am walking, the student is walking, there is water spill on the floor. He fell down. Why he slipped when water is there? Why he didn't slip when water was not there, or where water is not there? So these small things, if you can inculcate into the mind, a student of class school will develop a scientific temper in himself or herself, and by that, tomorrow he'll become a scientist by choice, not by chance. He will become a scientist by choice, and with that only we can take science to a new height everywhere. So again, I would like to thank Dr. Somen Ghosh for giving me this privilege, and I wish a grand success to this training program. Thank you very much.
Thank you, Professor B.B. Misra. Now I would like to request Professor Arnab Bhattacharya for inaugural address, sir.
Thank you all, and it's fantastic to be here. Could I just request people who are not speaking to mute themselves, please? There is crosstalk from at least Rashmi's mic. Can you mute yourself? Host, can you please mute people? Whoever's the host, can you please mute people?
Yeah, we're doing that. Yeah.
Okay, great. Great. Yeah, it's fantastic to be here this afternoon. National Science Day, the day we celebrate science. Of course, for somebody like me who is a scientist and a science communicator, it's not this one day, right? We live, we breathe science. And what I like to tell people, especially students and teachers on a day like this, is yes, we need these days to celebrate, but we should never forget that science is something that drives our world today. Whether it's the mobile phone in your pocket, whether it's a solar cell, all of these things are basically products of science, and often of science done many years ago or decades ago without thinking that someday this will be used. When Einstein came up with his theory of relativity, he didn't know that one day everybody would have little, phones in their hand with GPS things or get a taxi to come to their doorstep, relying with the GPS system, using the equations of relativity to correct for the fact that they're not sitting on the earth, right? He just did it for the love of science. And the problem I see in science in India is that we think it's a subject that you read in a book give an exam, and then forget about it. No, it's this exploration of the very beautiful world we live in. And this world could be a cell inside my body somewhere. It could be a planet orbiting a star in a galaxy far away. Everything, understanding how this world works, is science, and there is beauty in it. And a lot of it can be done very simply. I'm a person who likes to show science to people. In fact, let me show you something. I mean, there's some paper on my table. The simplest experiment you can do is just a sheet of paper. You can take a sheet of paper and you try and tear it this way versus 90 degrees away from it. In one case, the tear goes nearly straight. In the other case, the tear is very jagged and it usually goes off at an angle. That's a very simple thing. Now you ask, why does that happen? And that brings me to the final line. My tagline is always ask why, because it's only by asking whys that you can become a wise person. So happy Science Day, and thank you for having me here. We're going to have fun, and we are really happy to team up with the Regional Science Center to bring you some fun experiments that we've developed at TIFR over the years. Thank you.
Thank you, sir. Thank you for your encouraging words. Right now, Daniel Sim has been Australia's Deputy Consul General in Kolkata since December 2019. Daniel is an experienced policy officer and economic analyst at the Australian Department of Foreign Affairs and Trade, where he has worked since 2005. In Canberra, he facilitated Australian engagement in the G20, APEC, and World Economic Forum, and advanced Australia's relation with the countries in East Asia, including Vietnam, Malaysia, and China. He was the Deputy Director Economic Policy at the Australian office in the Taipei from 2008 to 2011. Daniel has a Master in Public Administration from Lee Kuan Yew School of Public Policy in National University of Singapore, where he was a Lee Kuan Yew Fellowship holder. He was a Bachelor of Commerce and Diploma in the Modern Languages Chinese from the University of Melbourne. The Consul General in Kolkata is responsible for advancing Australian interest in the eastern and northeastern Indian state in West Bengal, Arunachal Pradesh, Assam, Bihar, Chhattisgarh, Jharkhand, Manipur, Meghalaya, Mizoram, Nagaland, Odisha, Sikkim, and Tripura. Right now, I would like to request Daniel Sim, Honorable Deputy Consul General of Kolkata, to for address or chief keynote for chief guest.
Okay, Namaskar from the Australian Consulate General in Kolkata. Thank you so much for inviting me to today's inauguration of the Let's Do Science Festival, and really pleased to be able to support the Science Nomad, Dr. Stuart Colhagen, to present 3 sessions over the next week on physics, on chemistry and computational thinking to an audience of very interested and I'm sure engaged teachers in Odisha. So really looking forward to the sessions that are coming up over this week. And I know that the teachers in Odisha will get a lot out of Dr. Colhagen's entertaining, informative, enlightening sessions to make science alive. And it's so important, obviously, in trying to motivate and inspire the next generation of students about how important science research and technology is in our everyday lives. And so I think we'll all benefit a great deal from how Dr. Colhagen explains really sometimes both simple and difficult concepts, and then how to make it accessible and engaging for students to learn and then be able to apply it in their own lives. So that's about all I want to say. As I said, we're really delighted to be able to support Dr. Colhagen again to engage with the Regional Science Centre in Bhubaneswar, and also hope that in addition to be able to deliver these sessions virtually, he'll be able to come and visit Eastern India again soon. I know he's visited Kolkata a few years ago, and I'm sure that the Science Centre would welcome him being able to visit Bhubaneswar. And it's now possible with the borders between Australia and India reopening a couple of weeks ago. So that's all I want to say for today, and really look forward to the sessions ahead. Thanks so much.
Now the first session, Dr. Stuart Colhagen. Prior to the session, I would like to introduce Dr. Colhagen, who has delivered hundreds of training sessions for educators across India and globally. Before that, he was the Director of Science and Learning in Queenstown, Australia National Science and Technology Centre. He pioneered science exhibit development, shows, and educational program. He's only non-American to win converted iron science teacher. His passion is for applying science of learning to the learning of science. His motto is humble materials, powerful learning. Now it is over to Dr. Stuart. So this is your time to take up the session. Thank you, sir. Prior to that, I would like to convey my sincere thanks to Daniel Sim, Professor Arnav Bhattacharya, Professor B.B. Mishra, Dr. Ellen Pari for support. With collaboration, this program we were able to conduct on behalf of Regional Science Center. I would like to convey my sincere thanks to all once again. Thank you.
Thank you so much to you and all of the partners. Education and learning is so important. It's great to have such significant partners working together to collaborate to try and reach the scale that we actually need to go and lift communities. So a particular thanks to the National Council of Science Museums and the regional centre there, the ministries that are collaborating, and of course, a perpetual thank you to the great support that I've had from the Australian Diplomatic Corps in India for a number of years now. Indeed, I have visited Calcutta and worked there a number of times. I've visited as far north in the east as Guwahati, but I've also gone as far south as some of the parts south from Chennai. And when things allow, I'm sure I'll be heading back there as well. One of the reasons I'm always interested, always ready to engage with the education systems and the people that drive it in India is I feel there are a few places on the earth where people genuinely recognize that the path to improvement for themselves, their family, and their country is kind of unquestioned in India, that education is the pathway to reach that. I don't have to tell you of the challenges of doing that with such a large and diverse population. I think what we should do, what I should do this evening, is really share with you my approach to how we can support a small but very important part of students' educations. And my good friend that's joined us here tonight from the Chai and Why movement is, like me, embraces the importance of questioning. And so for this first session tonight, I'll be asking more questions than I'll be giving answers. Because for me, science is not a noun. Science isn't a thing. Science is a verb. Science is something that we do. Many school systems around the world, not just in India, tend to focus on sharing, delivering the nouns that come out of science, the facts of science. But all of the curricula around the world recognize and speak highly of the need for our students as they graduate to be critical thinkers, problem solvers, lifelong learners, communicators. We might call them 21st century skills. And some school systems find it challenging how to connect what happens in the class with the daily curriculum with these high goals. But those goals are really important. They're also skills more than content knowledge. And the only way to develop a skill is to practice it. So I could talk to you for 3 years about how to run well. But the only way to really run well is to practice running. And so the only way to really get good at problem solving is not to be told how to solve problems, but to practice solving problems. And it's a very different skill set. And so I hope for a little bit of your teaching time, you might change how you operate and reverse the direction. And rather than be sharing facts, you might share some questions. So let's start with probably one of my favorite simple questions. I might call them a provocation. I'll be provoking you to think a lot tonight, and I wish we could be more interactive and I could get your thoughts and your responses to these questions. Here is a flat mirror, something which we're all very familiar with, something which many of us are taught about the laws of reflection when we're at school. For any of you which might have missed those lessons, or perhaps they were a long time ago and we've forgotten, I'll give you an example of how we might teach the laws of reflection. And they really are very simple. Take me less than a minute, and everyone is guaranteed to get at least 100% on the exam. So this is very low stress. So we would share with the students that when we're dealing with reflections, that when light strikes a flat mirror at a particular angle, then the light is going to come off that mirror at the same angle, but on the opposite side. And we have all these sayings that kind of help us remember these facts, that the angle of incidence equals the angle of reflection. So now that I've finished my direct instruction about how we might talk about reflection in the school, if I asked you to answer the question, if light strikes the mirror at 45 degrees, what angle would it come off at? And I think without much delay, most of you will go, it'll come off at 45 degrees, which is good. If I told you that the light came in at 17 degrees, what angle would it come off at? Again, I don't think it would take you very long. You'd go, this is not hard. It would come off at the same angle, 17 degrees. If the light came in at 64.97 degrees, it would go off at 64.97 degrees. So we've kind of fairly quickly sort of mastered the laws of reflection. But I can then just turn the mirror around and shine the mirror so I can see the words, my logo on my chest. I can see my logo reflected in the mirror. And what do I notice about the words that are reflected in the mirror? We've all seen this. We're all very familiar with this. What do you notice about words reflected in a mirror? I can remember asking this question in front of several hundred students in a lecture theatre whilst I was in Calcutta. Everyone's hands went up. They go, oh, it's back to front. It's reversed. It's flipped. Lots of hands would go up and they would tell me that it's laterally inverted. And I would thank them for that, but I would also let them know that lateral inversion isn't the answer. Lateral inversion is the question. Why are the words that are reflected in a mirror only flipped left versus right, but not also top to bottom? What is it about a mirror that is going to flip the words left, right, but not top, bottom? And that's a question that will set you thinking. And it highlights the difference between being given some basic facts about science and about how we need to think about things we see every day and about can we actually understand them. And those things are very, very different. And I'm often asked when I visit India that one of the things which worries educators, that worries industry, are things like the number of engineering graduates that come out of the school systems. How ready are they for work? And different reviews suggest all sorts of different numbers, but that a lot of graduates coming out, very smart people, they've learnt a lot of science, learnt a lot of mathematics, but the industry feels they're not ready to work yet. And this is because we emphasize too much the facts and we haven't given them a chance to struggle and to think deeply and solve problems. Because engineering is nothing if not solving problems, but we need those sorts of skills everywhere. So I'm going to leave that problem with you, that question with you. And as a special gift, because it's Science Day, National Science Day, I promise never to answer the question for you. I will leave that with you. And tomorrow, when you come in to brush your teeth or comb your hair in front of the mirror, that question will come back to you to think about, what is it that flips the words left, right, but not top, bottom? When I work with students in a classroom, I will get lots of suggestions. And my response to every suggestion is not whether it's right or wrong, but that's an interesting idea. How can we test it? Because science isn't remembering the facts. Science is making an observation and thinking about how we can test your idea to see if it's true. That's really what science is. Science is doing. Science is that verb, that action word. So as a special gift, I'll leave you to think about the mirror and see what answers you come up with. Students might often go, oh, we've got two eyes. Our eyes are in this plane. I go, that's a good idea. Then I'll cover one eye. And it's still flipped. So that's not the answer. But explore it yourself, explore it with your students. The important thing is not the answer, the important thing is how they think about it. Let me perhaps now share with you another simple activity, one that's simple to do, but we'll see how you think about it. So here I have just a long, even stick. You could do this with a much shorter ruler. It's kind of even in weight distribution, so it's a uniform shape. It's just like a meter ruler. It's a little bit longer. And I'm just going to balance this stick on my hand, just rest it on top of my hand. And starting, if my arms are long enough, starting at each end, I'm just going to close my eyes and I'm going to ignore the ruler. All right? There is no ruler. It's a meditation test. I'll just ignore the ruler and I'm just going to slowly bring my hands together. I'm not going to use my thumbs to grip the ruler or do anything. The ruler will sort itself out. What do you think will happen if I try to move my hands together slowly? What might happen? What's your prediction will happen? All right, well, let me try. I'll close my eyes and I'm not doing it. I'm not paying any attention to the stick at all. The stick is just doing whatever it wants. And I'm not moving my hands up or down or gripping it. And we come to the balance point. We come to the balance point. Now, you might have seen some things where my hands moving uniformly. Just have a look again. And I'm not trying to do anything. I'm just moving my hands together. I can sort of feel the ruler sliding over one hand and then the other. And they come together in the center. So my question to you is to think about, why does that happen? What's going on? Why do they come together in the center? They certainly started at each end as I move my hands together, and they reach the middle. So maybe that's just because I started at each end. What I'll do now is I'm going to start with this hand, my right hand, very much closer to the middle. All right, so it's going to start with a head start. Will they meet at the middle, the balance point of the ruler, or will they meet halfway between where my hands are? try to meet over here. What do you think will happen? All right. Again, I won't pay any attention to what's going on. The ruler is just, it's not the ruler, it's just the world of science. Nature is sorting itself out. I come again to the balance point. So it balanced not because I started my hands at each end. It seems if I'm doing this, just about no matter what I do, they will come and they'll balance. But as I said, you may have noticed, you should have noticed by now, that my hands aren't kind of moving uniformly, coming in. One moves and then the other moves. So what do you think is going on behind that for an action, for an activity like that to take place? Why is it finding the balance point? Let's change things a little. And so that stick that we used before was uniform, even size, even thickness, even distribution of weight. Here I've got a broom, so the head is much heavier at this end, so it's not uniform anymore. What do we think might happen if I try that same activity with this? What do you think will happen? Will my hands try to meet in the geometric center, in which case the broom will probably fall, or will something else happen? What do you think? I hope and I expect many of you will try this later, and you'll try this with your school kids, with your students. All right, again, I'll just ignore the stick. I'm not grabbing it. It's just doing whatever it wants to do as I try to move my arms together. And I'm not choosing which hand is moving. I'm just trying to move them both together. And we reach a balance point again. So our hands have reached the balance point for both the stick and for the broom. Just try that again. As I said, I'm just moving my hands together. I'm not choosing which one moves. It just reaches the balance point. And there is actually a lot of different bits of science going on behind this. And there are things which you and the students can see and think and apply. Apply is such a big, powerful word. If you understand something properly, then you can apply it to a new problem. And it's that application of your existing knowledge that really is a powerful skill. Let's see how far we can go with things that are oddly weighted. So here is a heavy golf stick. Almost all the weight is up here. And we'll try that. And I really wish I could be hearing your thoughts at this stage. What's your suggestions about what's working? And again, without me trying to manipulate the result, we've reached the balance point. So what's going on? My hands are moving sometimes one, sometimes the other, and they're seeking the balance point. So we've got friction happening here. We've got forces and load from the weight of the stick pressing down on my hands. And we can talk about where the center of mass, where the balance point of the stick is. And so if one of my hands was at the balance point, at the center of gravity, it's a term which they will encounter at some point, then really all of the weight is acting here. So I can balance all of the weight here. If my hand is close to the center of mass, it will have most of the weight on this hand, on my right hand. This hand out here near the edge has very little weight on it. So what that means is because it's got very little weight, it's got very little friction. And so as I try to move my hands together, my left hand is the one that starts moving because the friction is low there. And as it comes closer, it picks up more weight because it's closer and closer to the center of mass. And at some point, it has so much weight that the friction increases to the point where it stops. And then the other hand moves. And then I take turns, swapping backwards and forwards, always getting closer and closer to the center of mass. And so with that, we reach the balance point. It doesn't matter what the distribution of weight is. So with something as simple as a broom, we can be exploring friction, what we call static friction, dynamic friction, forces, center of mass, torque. All of these concepts are here just in a stick if you want to explore them. So let's see whether or not we've got kind of mastery of the idea yet. And for a good activity with students, I feel you can always ask another question, go a bit further, go a bit deeper, so that the students which are quick to think through these challenges, these problems, you can always give them another problem and keep them working. Whilst some of the other students that are still struggling with these ideas, you can go back and give them some more help. So we call that sort of differentiation in sort of schooling. So the ones which are quick at it, you can keep them going. They don't get bored. So we've seen, and we've sort of discussed about why we come to the center. Now my question is the reverse. My question is the reverse. If I just close my eyes and the stick is balanced and I try to move my hands apart at the same time, what will happen? What will happen as we go backwards? What do you think will happen? Most of the students and most of the teachers that I work with, when I come to this point and I ask them what will happen, they will go, oh, your hands will reach the edges at the same time, and then the stick will fall. And it's reasonable to think that way. Let's just see what happens. All right, I'll just close my eyes and I will let the stick decide what it's doing. One moved and it would just keep moving. We'll try it again. Find the middle. And it won't always be the same, but the first hand that moves just keeps moving. And so the forward and the reverse process is not the same. So there's one process that happens as we move in. It's a very different process when we move out. It's the same physics, but it has a very different result. So here, both of my hands are supporting the center of mass. So that they have about equal weight, about equal friction. But it won't be perfect. One will have either a little bit more weight or one hand will be a little stickier than the other. And the moment one hand moves, it's now further from the center of mass, so it has less weight on it, which means it has less friction. And it doesn't matter as it goes out further, that only gets more and more the case. And so it will never swap back to the first hand. And for many of us, when we've tried this experiment going forward, going into the center, many students will have such a strong expectation that the right answer, the expected result, is that their hands will come off the ends at the same time. That is such a strong idea that when I get them to this point and they start moving their hands out and they see that one hand is moving and the other one isn't, they often can't help themselves but starting to roll one hand along to influence the outcome. It's mostly subconscious, or they will start gripping with a thumb to stop this one moving so the other one can go out, to make it do what they think it should be doing. And that's also a wonderful teaching moment for the students, because it's about fairness and accuracy in the scientific process. That sometimes if we really think we know the answer, we struggle not to influence the experiment, because that's what that is. That's an experiment, a very simple experiment. And the students think they know what the answer is, and they are doing what they can to get the answer that they are expecting. They're not just letting the experiment run and see what the data is, see what the answer from the experiment is. And for someone that's going to go into doing real science, that's a really important lesson to learn. That the experiment has to speak, and we need to work very carefully to keep our bias and our expectations out of the experiment. Otherwise, it might be deliberate, or it might be subconscious, unconscious bias. We can actually manipulate the results, decide that we don't like that bit of data. That was a bad result. I'll just throw it out, because it spoils your idea about what the answer was. So these activities might just involve a stick, but the learning and the messages about how science can be done and how to think about things and to pose those questions and get the students to have at least a little bit of time exploring their ideas about how to explain it. In a lot of our teaching, we run the other direction. We tell you what the answer is. We may do a demonstration to show you that we're right, and you've got to remember it. Here, if you can just change around even a little bit of your teaching, still teaching the same topics, but first get them to experience something that you're talking about to them, and get them to think about it, get them to try and explain it, even if you haven't taught them the science before. It's a real phenomena. They've experienced it. They will have some ideas about it. And the process that I use when I'm encouraging that sort of 21st century skill is really get them to look, get them to think, get them to propose ideas, and to ask them how they would test if their idea is true. Get them to think critically. Does their idea explain everything we see? And that's, again, another very important and powerful lesson to pick up from science, even very, very simple science. While we're talking about sticks, let's have a look at another balance activity that I'm pretty sure is in the textbooks in a number of the Indian school systems, the state school systems. And this is certainly an activity that you would be able to do in your classrooms. For the most part, I try to use very simple material, because the questions then are more meaningful. So here's a stick. I'm just going to turn this into a balance, just like a very old-fashioned simple balance. So a stick on a string. I'll just go and hang that up here, and should be reasonably balanced already. Kind of balanced it up today. And this activity that we'll look at now, just choose a balloon that we can see against the black. I've got two balloons, yellow and a pink, and I'm going to suspend them on the balance and balance it up. I'll blow the balloons up to be as close to each other in size as I can. And this is really a question about whether or not the students think that air has weight. All right. So we'll blow up the first balloon. I've learnt from my many visits to India, if you give someone from India a balloon to blow up, they always seem to try and blow them up sideways. All right. nowhere else in the world blows up balloons like that. And I really don't understand why that's the way it's done in India. But everyone will blow up a balloon sideways in India. It works. It's perfectly good. Just an observation. All right. So I've blown up one balloon. Certainly I've put air in there. I think you will have heard that. And I'll blow up the other balloon, the yellow one, same to about the same size, as close as I can make it. Okay, I'll tie that off. So both of the balloons have air in them now. And I'll hang these on the balance. There we go, just on a clip. Put that on the other clip. We'll see if we've got it balanced. Let's just leave it there for a moment. The air in the room is fairly still. And I think I've done a pretty good job of getting those balloons the same size. All right. So we now have two balloons on the balance. And my question, and perhaps some of you have seen this activity, maybe you've done the activity. As I said, I'm pretty sure it's in some of the textbooks, the curriculum materials that I've seen in India. So my question to you then is, if I carefully let the air out of one of the balloons, what will happen to the balance? Okay. If I let the air out, what will happen to the balance? What do you think will happen? So I've got some very sharp pliers. I'll just make a small cut in the balloon. I'm not going to burst it. It's not going to throw the rubber everywhere. At least that's my hope. I'll just make a small cut, let the air out gently. What do you think will happen? Will it stay balanced? Will the one with the air left in it be heavier and go down? And more importantly, what does the experiment that we just will do, what's it going to show us? What do you think it shows us? All right, let me take the pink balloon. I'm just going to put a little cut here and hope that it doesn't burst. All right, so it's balanced beforehand. I'm not going to let it fly around as the air comes out, otherwise it will just be a jet and it'll disturb things. So they were balanced before. I've let the air out. Are they balanced now or are they unbalanced, and which way? It's a lot more fun for me if I can actually see the teachers and see their comments. So I'll let go. 3, 2, 1. And we'll just let it even out. Don't want to be seen to be influencing it. And perhaps not surprisingly, I'll bring it around this way so you can look front on. The balloon with the airlift in it is hanging down, so this end is certainly heavier. And so the textbook answer, and if you go online to look at YouTube clips of science activities, you will see a lot of activities looking at this demonstration and going, this shows you that air has weight. And that's certainly what it seems to be showing you. These were balanced. I let the air out. This has gone down. This end's got to be heavier. And that's true. But let's look at one more activity. All right, using the same balance. I'll take the balloons off for the moment. We'll take the balloons off. And maybe for this activity, I'll just get rid of the black curtain, because what I have is some black plastic bags that I want you to be able to see against the white. And so what I have here now are a couple of large black, we would use these to line rubbish bins. So the plastic is fairly light, but they'll hold about 50, 60 litres of air if we're careful. So I'm just going to hang these. The plastic bags should very much be the same weight as each other. I'll just check that that's the case and that they are balanced. Please be balanced. If I get out of the way, you'll see they're balanced. All right, so this one and the other one, bar is nice and balanced. They're both fairly flat. I don't have air in either of them. So if that demonstration, if this balance is showing that when something is full of air, it's heavy, as we saw with the balloons, if that's true, when I fill up the bag, with air, tie it off, that should be heavier, okay? Because that's what we're just doing with the balloons. The balloons are a little easier. So I'll just take this bag. Don't want to disturb the balance. So when we put it back, it's a fair test. All right. So now I've filled the bag up. So that's a lot of air. That's a lot of air. And sealed the mouth. We'll hang it on here. And kind of 3, 2, 1. I hope you can see the bar. The bar is perfectly balanced. The bar is perfectly balanced. The bag that is full of air weighs the same as the bag that's empty. And it's not a trick. That's what really happens. Try it yourself in a room where the air is fairly still. And your students might go, oh, you haven't sealed off the top. If you want to, you can put some ties on there and seal it off. What's actually going on with that activity is that the example that is often shown using the balloons does not show that the air has weight. Air does have weight, I believe that, but this doesn't show that air has weight. Not with that test. Because here I filled this up with 60 litres of air on the balance. It's made no difference. What's going on? What's the explanation? What have we missed? Have we missed something? What could it be? Some of you might be going, oh, there's something you breathed into it. Maybe there's something to do with the CO2 in your breath, water in your breath. They're all good ideas. And my answer to that would be, how could we test then if that's the effect? And someone might think, oh, we could use a bike pump to blow up a balloon so you don't have any CO2 or moisture from my lungs. the activity as we've just seen it would be exactly the same. What this is really showing us, this demonstration with the balloons, is not that air has weight. It shows us that the air in the balloon, which is compressed and under pressure, is denser than the air in the room. Because we're weighing the gas, we're weighing the air in this bag in a room that's already full of air. So it's like weighing a bucket in the water, if you like. It's already in the fluid that this is supposedly supporting. And so this is something which I like to share with students and spend some time getting them to think about it. Because later on, or if before, they've been taught about buoyancy and objects floating, then this is a really good thing for them to take their knowledge and apply it to see if they can understand and explain what we were just seeing. But if you weigh air in air, it doesn't have any weight. It's already neutrally buoyant. It's already floating. Just as if you took the two balloons into the water, an empty balloon in the water would weigh the same as a balloon full of water in the water, because it's neutrally buoyant. It's in the same fluid. It's only because the air in the balloon has compressed, because the rubber is giving us a force to work against. It's only because the air in here is compressed. So what that demonstration shows us is compressed air is denser than normal air. So it's a good demonstration of that, but it's not a demonstration that air has mass. Because if you actually try the demonstration without compressing the air, you don't get a result. So I think that's one of the misconceptions that might be worth you kind of exploring. Think through it yourself and challenge, some of your students also to think about what's going on. It's very common for us to forget that we're already in a fluid, that we're already in the air. While I really like that demonstration, to me, it really drives some thinking. And again, for me, when I'm doing these activities, the goal is really to get you curious and to get you thinking hard, thinking slow about things. Not just trying to apply a formula, but to see if you can actually understand and explain what you're seeing. Because there's nothing complex in what we're setting up, but it is still a challenging thing to think through and explain. So hopefully you like that, perhaps nearly as much as I do. I think it's a wonderful demonstration which can lead students to be thinking about many different parts of their science, about density, buoyancy, flotation, pressure. There's a lot. While we're dealing with balloons and pressure, I think I'll bring this activity out to share with you. You can do it with relatively available materials. In this particular case, I've just got a tube. We have our irrigation systems for our lawn, our gardens. And so we have these kind of little taps, little valves, which we can use to turn on water to water one part of the garden or another. You may have seen similar things there. I'm not sure. So here, two balloons, some tubes here, which can be connected to each other, and I can open the valve to let the gas flow. So if I open the valve, I can blow all the way through out to the other end. And on each end, I've just glued a bottle top, because I'm going to blow up the balloons, put them over the bottles, and then we're going to have a little bit of a tug of war, or sort of a push of war, maybe, a push of war between the two balloons and see who wins. So first thing is I'll turn the valve off so it's blocked, so the air can't flow from one to the other. And for the white one, I'll blow it up about that big. Now I'm not tying it off permanently, I'm just twisting it so I can stretch the mouth of the balloon around the bottle top. This is one of those activities which you need to practice if you're going to do it by yourself, one-handed. But we're there. All right. So balloon blown up sort of medium big is kind of sitting on one of the bottle tops. So if I opened up this, then the air would certainly come out of the balloon and just leave the other end. And the pink balloon, I'll blow up just a little. So there's our white balloon, and the pink balloon is blown up, but sort of nowhere near as much. So I'll twist that off. I'll see if I am agile enough to get that over the bottle top without letting the air out. Success. All right, so I'll just stand back so we can see both. So we've got the small pink balloon and kind of the medium-sized white balloon. In a moment, I'm going to open up the valve so that the air in both of the balloons can work against each other. So they're both under pressure. What do you expect to happen? Is it easier to blow up balloon big or small? So what do you expect to happen? All right. It's a small valve. It'll take a little while for any air to flow. I'm going to open the valve. And most of us would normally think, oh, okay, they will even up. The pressure in the big balloon is high. Pressure in the small balloon is low. They'll even up. But the opposite happens. The opposite happens. And that's normally surprising for all of us. It was certainly surprising for me when I first saw it. How do we explain that? What's going on? What are your thoughts? What do you think your students would think if they saw that? Is it harder to blow up a balloon to make it bigger? As you're blowing it up, does it get harder or does it get easier? You may have all sorts of different ideas. I'm sure your students would have many different ideas. The answer behind all of this, or the truth, perhaps more than the explanation, the truth is that the pressure in a small balloon is higher. The pressure in a small balloon is higher than the pressure in a big balloon, provided you don't blow the big balloon up to the point where it's about to break. Okay, so if you make the big balloon too big, it won't give at all. So small balloon and a medium-sized balloon, the pressure in the small balloon is higher. That must be because it pushed the air from here into the big balloon. And that might be, oh, the rubber was thicker, it wasn't stretched so much, it's not the pressure in the air. But the only place where the force was being delivered was through the pressure of the air. Tube is the same size. The pressure of the air at this end was greater, or it wouldn't have flowed in that direction. You can explore why you think the pressure is greater here. But in fact, that's true of all bubbles. So if you did this experiment with soap bubbles and connected them with a little funnel and a tube, you would see the same thing happen. That if you connect a small bubble to a big bubble, the small bubble will get smaller and the big bubble will get bigger. And in one way, we kind of know that, or we've heard some evidence that kind of supports what I'm saying. And that is, if you blow up a balloon, and if I hold the balloon here so it doesn't fly around the room, but I open the end I blew up and we listen to the sound, just listen very carefully to the sound. Hopefully it'll make the right sound for me. Now, if you pay very close attention to that sound, the sound towards the end goes, the air leaving the balloon towards the end gets faster and faster. It's under more pressure as the balloon gets smaller. Seems sort of counterintuitive, but it's the truth. So that demonstration I showed you kind of shows that the pressures are different. There is, I think, a wonderful challenge to go and give yourselves. And if any of you are teaching perhaps grades 10, 11, 12 physics, these kind of problems to think about really are powerful chances for the students to practice their problem solving, for you to step back and not give them answers, but to hear and to listen to how they are thinking about the problem. And this is a much better way of you getting to understand whether or not the students are remembering the formulas or whether or not they're actually understanding the concepts. Because most simple exams don't actually tell us that. A simple exam won't tell you whether or not someone just remembered the formula, because that's what they're good at, or whether or not they understand the principles and can apply them to a new situation. So problem-based learning, or these sorts of little challenges, are very useful for as an educator to actually recognize where the students have strengths and where they might need help. Here is a great simple question to go and give a group of students. Just blow up a balloon. Maybe you blow up some balloons small. You blow up some balloons so they're larger. And students, I'm sure, in senior high school and grades 11, 12 certainly, will have certainly been exposed, if they're doing physics or sciences, will have been exposed to the formulas of pressure. The pressure equals force divided by area. You'll probably express it that way or some very similar way. So my challenge to the students, to you as well, is if I've blown up a balloon, how are you going to work out what the pressure is in the balloon? All right. Use any tools that you think are reasonable that you might have. In a normal student's bag, there's actually probably enough tools to work out an answer. But think about that as a problem. I've given you a balloon. Perhaps I've given half a dozen students balloons of different sizes. And I've asked them, how are you going to work out what the pressure is? Not tell me that, oh, it's under pressure, but actually what the pressure is. How are you going to measure, give me a value for the pressure in a balloon? Can you apply the formulas that you understand? Can you apply your understanding about what pressure is and what pressure means? Can you apply that to come up with an answer to tell me what the magnitude of the pressure is in a balloon? How would you do it? And there are many different ways. There are many, many different ways. Some are very simple, but I'll leave that for you to think about how you might work out what the pressure is in a balloon. If you've got any good ideas about that, interesting ways to work it out, feel free at any stage to contact me, connect with me. Easy if you want to just get in touch on Facebook and just sort of look for the Science Nomad on Facebook. There's a Science Nomad page there. Or through Twitter, again, Science Nomad, you'll be able to find me, or connect with me through the Science Centre there. If you've got an idea about how you'd measure the balloon, I would love to hear your ideas. And if you get a chance perhaps to put that question to your students or some of your friends, I'd love to hear how they would give you that answer. All right. So we'll be working all week. I'd love to see if anyone's worked out a way to give me what the magnitude of the pressure is in a balloon. While we're kind of working with pressure, because pressure is one of those things in physics which we will do a lot of teaching on, and there are some challenges for students to sometimes think about pressure, static pressure, moving pressure. What we might look at sort of quickly, I'm just keeping an eye on the time so we can get through a few of these different types of activities. One of the kind of standard demonstrations that is certainly in the textbooks, and you may get a chance to do in the classroom, when we're talking about pressure, just comes to the topic of, well, the tool of just using a syringe. All right. So these days with COVID, we're all very familiar with syringes. Here in Australia, because we really want to get on top of COVID, all of our vaccines are done using syringes this big, okay? Just waiting to see if anyone believes that. We don't have vaccines in Australia that big, the normal size. It was just a joke. But here is a syringe. We can do a lot of exploration with pressure if we have some syringes and just some tubes. So depending on your school and your location, you might be able to find some of these. One of the things which is great to do with a syringe when you're working with the students, pull the syringe out, just block one end and get them to squeeze the syringe in, and they can feel that the air is compressible. And that's one of the really important concepts. Air is compressible. It's what was happening in our balloons. You can feel it. If you squeeze it, it goes in. If you take your force off, it comes back. A lot of science happening just in that. If I took the syringe and sucked up some water and blocked the end and tried to compress it, I won't get anywhere. And so that also is sort of a strong introduction to what's going on with pressure and the differences between water as an incompressible, effectively incompressible liquid, and gases and the gas laws and all of those things. If we're dealing with sort of pressure in fluids, one of the sort of versions that you will see in a textbook, it might look a little bit like this. I've got a 10 ml syringe and a 1 ml syringe. I've just connected them just with a tube going from one to the other, and they're both full of liquids. We'll just change cameras now, and we'll look at this from my workbench. So at the moment, we're looking down onto the workbench, just in case you're disoriented, perhaps. And we'll just put a little bit of color contrast under there so you can perhaps see what's going on. And this is a powerful device to go and introduce students to what's happening with pressure. So big syringe, small syringe. There is kind of the intuition that that means that a big syringe with a lot of water should generate a large force. And certainly if we push this in, the water is going to go through here and be communicated over here. The water will flow over here. The pressure, which we will keep telling our students, is kind of the same everywhere. But if we push that in, it only needs to go in a little bit for this to come out a long way. All right. The reverse, when I push this in, this must come out. Water is incompressible, but you will probably barely see this move because this is going to travel all this way. They'll just have 1 ml of water going into here. Perhaps you did see that. I can do it with negative pressure. I can pull this out and pull it in. But also really importantly is that students can grab both syringes and now they can directly feel just in their own hands kind of what's going on. This one over here, this little syringe, very easy to move in and out. I can't I don't have enough strength in this hand to stop this syringe pushing this out. All right, I can try as hard as I want. This hand isn't even breaking a sweat, as we would say. It can push in, no problem. And so this is one of the ways to give the students we would say a gut feeling, a physical intuition, because a number of kind of the set problems, the set exercises, so the exam questions that are almost certainly going to be in the standard exams, will be getting them to go and take these sorts of situations and to try and get them right. And so if you can get into their hands an experience like this, they might remember, oh, there's a ratio here that's to do with the surface areas of the pistons. I remember that, but I can't quite remember which way around it goes. And their intuition is that this must provide the big force. It's a big syringe. I can push on it hard. But in fact, that's not the way it works. And so giving them this intuition, they might remember back to, oh no, this was the one that was easy to move. So this force is overcoming that force. So that can help them even with their formal exams and gives them a much better, different understanding of it. And that will help them through many of their activities. You don't need the wood. I just need that because I don't have enough hands to hold all of the bits. One of the kind of extensions to that, which I sort of like to pose to my learners, just to get them thinking, because I'm very, as you know by now, I'm very interested in getting people to think about what's going on. So here, same situation, very large syringe, large surface area, slightly smaller syringe, and I've connected them up with water, with a tube. It's got water in it. I've just put blue dye in there so you can just see the tube a little bit easier. And sure enough, if I push on the big syringe, the small one will come out. Small one's easy to push in against this. And so we've got that experience. If you or your students have a feel for what's going on, I then would pose the following situation. You can see where the two syringes are up to and their ends are still connected, but I've just put their plungers, the handles together. And now I ask the question, what will happen if I try to push both of the syringes towards each other? What's going to happen? Will nothing move because water is incompressible? Will one of them move? If one of them is going to move, which one? All right, so this is a 10 ml syringe. This is a 60 ml syringe. If I push these together, if I try to push these in as sort of a push of war, not a tug of war, what's going to happen? Nothing. One of the syringes will move in. Which one? What do you think will happen? I'll just let you think about that for a moment. Which one wins? Which one loses? Or do they just stay the same? What do you think will happen? So again, take these two, push them against each other. What happens? And if you've got to the point where you truly kind of understand, if you truly understand what's going on with the pressure and the force and the movement, you should be able to work that one out. All right. So that's an exercise. And these exercises, I think, are for everyone. It's not just those students you think are bright or they've got all their other work done. This is a great way to inspire curiosity and to get students to think about it. If they want to put it together and test it to work it out, that's perfectly fine too. That's not cheating. But once they've seen it happen, then the next step is, how do you explain what you saw? One thing is getting the right answer. Another one is explaining what you saw. So think about that. And maybe, again, if you've got some ideas, some answers, you can send them through to me and we can sort of perhaps talk about those, or I can go through that next during the next session tomorrow evening. All right. We've been talking about pressure. So let's also look at one of the applications. Look at one of the applications that we can make of pressure, and it's a useful one because it relates to a number of areas in our physics teaching, in our science teaching. So here there's just a water bottle, a drink bottle. This used to have a carbonated drink in there, like a lemonade. So the plastic is a little bit thicker, a little bit tougher than just drinking water bottle, plastic bottles. Just kind of makes it a little bit more rigid. And all I've put into that is some water, again with some food coloring. And I've drilled a hole, and I think many of you may have done these activities yourself, built these yourselves. Put a straw through there, a bit of glue to go and seal it to make sure it's airtight. And the straw goes into the water, and you can see there on the camera that the water level at the moment is up to here. All right. So what we'll do is we'll just have a quick look on the workbench at what sort of happens with this bottle. So here's the water, the cap is on, the air can't get out, the water level is here. So my hands are warm compared to the room and the bottle. So I'm just going to bring my hands close to the bottle. I'm not going to squeeze the bottle. I think we all know what would happen if I squeezed the bottle. But I'm just going to lightly rest my hands on the top. In fact, you can see, I'll move it further back because the water is going up so quickly. It's almost reached the top. And when I take my hands off, the water slowly comes back down. It wasn't because I was squeezing the bottle. If I took my hands off and I was squeezing the bottle, the water would just come straight down. So here we've created a relatively sensitive thermometer. And that's a useful learning activity in itself. We can now talk about expansion and heat and gas laws. So we can see that the gas here is expanding because as that expands, it pushes on the water and that pushes the water out. But it also means then that the students have created a measurement tool that they could use to go and investigate all sorts of things to do with heat. So they could build model houses to put outside in the sun and see which houses heat up faster and not. So you can use laboratory thermometers if you have them, but I'm a big fan, even if people have got the resources to buy digital temperature, digital thermometers or whatever, that actually putting it together yourself, you can go home and make it. You can understand a lot more about what's going on. So just try that again. On a night like this, I probably don't even have to touch. See, I'm not even touching the plastic, and just the heat from my hands is warming the air inside the bottle. It's expanding. If I touch the bottle, we'll transfer heat faster, and it will rise very, very quickly. And so we've made quite a sensitive thermometer. So I think that's to me is a great learning activity. We can sort of extend the topics which we cover in our physics. I know in a lot of schools, if you're teaching physics, you're teaching physics. If you're teaching chemistry, you're teaching chemistry. If you're teaching maths, you're teaching maths, and there isn't a lot of crossover. And that's a pity because there's a lot a lot of all of these subjects, which, you know, they share important concepts. What I want to sort of share with you now is another activity. Here I've made two thermometers, pretty much the same. They're certainly similar enough for us tonight. And I've got here a sheet of that same black plastic that was in those bin liner bags. It's a particular, frequently it's a particular kind of plastic. It's polyethylene is what the bags are normally made from. And I'm just going to put this bottle into shade. So I'm going to shade it. All right. And just to make sure its shade skirt stays on, I'll just a little clip on the back just to make sure that it stays shaded. And the water level in this one is about here. This one is perhaps a little lower, so it's starting a bit further behind. And what I'll do in a moment, and you'll certainly see it, just move the camera there for a moment. There we go. Is I've just got a small lamp. All right, it's only about 40 watts, and I'm going to shine that light onto both of those bottles. I'm going to do the best I can to make the illumination of these bottles the same. What do you think might happen? What do you think the difference might be between those? I'll turn the light on in a moment, and it's about a 40-watt globe, so there's a little bit of heat in it. What do you expect to happen? Will the one in the shade warm up slower, the same, faster? What do you think might be the result? All right, 3, 2, 1. The camera's reacting to that. We'll see what happens. This one's already sort of come out of the top of the bottle, but as I said before, it was already ahead. This one's now emerged and it's racing up and up. It's pulling well ahead. In fact, it's even bubbling out from below. It's actually burst the glue seal on the bottle. Just turn the light off and let that run back in that other direction. What we've in fact created there, in fact, is a very good model of the greenhouse gas effect. All right, so we've made a model of the greenhouse gas effect. That plastic that I used, the black plastic that I used, looks black. It is black. It's black in visible light, but this particular sort of plastic lets infrared light through, infrared radiation. That's the radiation that we associate with heat. All radiation transmits energy, so all radiation transmits heat. We just think of infrared as being heat just because we don't see it as being light as well as heat. But while this is black to visible light, it's actually transparent to infrared, almost completely transparent. And that's a similar property that we have with CO2, carbon dioxide in the atmosphere. It's a little bit more complicated than that with carbon dioxide, but not very much. The model is still a very good model. And so with lots of greenhouse gas, CO2, or this plastic, the infrared can actually go through, heat up the objects inside, but catch and trap that heat, real thermal heat on the inside. And so you can do this experiment without the heat lamp. You can just take it out and put it in the sun. You'll get exactly the same result. And you'll find this kind of black plastic sort of bin liner reasonably easily available. It's fairly common, unfortunately. But this kind of polyethylene, polypropylene also, but these are normally polyethylene, is transparent to infrared. We can, in fact, if you've got a, there it is. These days, I think we're probably, unfortunately, all too familiar with infrared thermometers, checking people's temperature. Fortunately, we have these, but we'll see what my temperature is at the moment. So 33.1. I must be okay. If I just hold the black plastic up and try and get its temperature, it's reading 26.8. It's pretty much reading the temperature of the room. Might even be reading, so 25.8. It's pretty much reading the temperature of the room, the temperature of the curtains. But if I just put this not touching my face, but just in front of my face, and I try to take a reading, what we'll see is the temperature it's reading seems to be 31. It's because it's measuring infrared radiation. So it's actually measuring my body temperature coming off pretty much through the plastic with very little of it being absorbed. So it's going through, this is seeing me through the black plastic, all right? So if you've got access to one of these, that's another extension activity that you could certainly think about doing. So that's some interesting things to think about heat. We've got time. We'll look at another, it's kind of heat-related question, and we'll just set that up over on the other workbench. So we'll just put these thermometers away. Interesting that one of them leaked on me, but that's okay. So for this next activity, what I've got here, and we'll sort of bring the camera in so we can get a slightly better look at it. So I have a piece of wood and a piece of solid aluminium, and they've been sitting in this room together next to each other. And I think most of us have had experience of, touching various things in the room, the metal on a chair, perhaps the glass on a glass tabletop. And the glass on a tabletop in a room very often might feel cold. The fabric on your chair or your couch, your lounge, might feel warm. And so our senses tell us that the glass is cool, the timber is warm or medium, and sort of the fabric on the couch is actually warmer. But that's another reason we do science, is because our senses often let us down. So here again with the digital thermometer, reading the temperature of the block of wood, comes in at saying, if we can just get that so you can see it, you should be able to see it. Hopefully you can, or you might just trust me. The block of wood's reading about 25.6, 25.5 degrees. The aluminium, which to my hand feels cold, it's reading 25.7 degrees. They're the same temperature. That feels room temperature. Doesn't feel hot, but doesn't feel cold. That feels quite cold. But they are the same temperature. And that's also something to put as a question to students. You will probably have taught them about things that conduct heat and things that don't. and they will know a certain amount of that. But can they give you a good explanation as to why these two sitting in the same room, one feels cold, one feels warm? What's going on with that? What do you think the explanation to that might be? And you might have some answers, but what do you think your students might suggest? What might they propose as an answer? One of the things we can do with these materials here, I'm just putting a rubber band on there to stop a block of ice running away, and put another block of ice on there. So 2 blocks of ice. They've come out of freezer. They'll be the same temperature. Just put that there just in case it tries to get away. The aluminium feels cold to my hand. The wood feels warm. What will happen to the 2 blocks of ice on those 2 materials? The room is certainly warmer, and they are certainly warmer than ice. So we're going to assume that the ice is going to melt. What do we think the difference might be? What would you expect? What do you think your students might expect? And this is a fairly simple activity to do. You can find a range of different materials, not just wood and aluminium. Probably should not be too hard to go and get some blocks of ice prepared overnight. I can see what's happening over here. You might use what's happening. It does not take very long for there to be a useful result. While that's happening, we'll just give it an extra minute. Show you another demonstration, something which you can do if you're interested in pressure. So here is our syringe labs. These sorts of activities, I try to get some very big syringes. Here in Australia, if we go camping, we go out into the bush, we might bring some marshmallows. So we would typically take these if we've got a fire, and we would kind of toast the marshmallows. And normally we'd end up burning our mouths because we get these so hot and they're melting sugar. So a marshmallow is kind of whipped sugar and air. So they're, light, fluffy, spongy, kind of rubbery creations, which I don't actually like very much myself, but lots of people do. And they're so big, or those ones are so big, I've had to cut it down a little bit. And I'm just going to put it in to my syringe, which presents its own challenges. It's resisting me, but I will win. May take a moment, but I will win. So put a marshmallow in, and we can actually see, if we wish, what we've been talking about with that expanding air. So it becomes a way to visualize what's going on. So again, I've just got a little tap on the end. I can put my finger there, but it kind of hides everything. So I can close the tap, and when I pull back, we would know that the pressure is going to go down. And so let's just try that in a place where you can see what's going on the camera. You might be able to see both as I squeeze in that the marshmallow shrinks. As I pull back, the marshmallow expands. And if you've got a vacuum pump in your lab, which you probably don't, you can actually do this to an enormous extent. Let's go back and have a look at our ice on the wood and ice on the aluminium. So what do you think would be the difference? The wood was warm, the aluminium was cold. We'll go back and have a look. There's almost no ice left over here on the aluminium. Even though the aluminium felt cool, they were both the same temperature. There's barely any melt water on the block of ice over here on the wood. Still feels warm. Still feels cold. In fact, feels very cold. But the ice on the aluminium has melted completely. This maybe 5–10% has melted. Same room, same temperature. And this again, I think, is a good puzzle to put to students. You may have done your formal teaching, talking about conduction of heat. You may have even done, depending if you're doing physical chemistry or physics or chemistry, you may have even done things about specific heats. If they've had that exposure to those concepts, even perhaps beforehand, showing them something like this and getting them to think about what the explanation is a good way of priming their curiosity, so that when you come back to perhaps formally instruct them about what the science principles are behind it, this has been sort of a question, at least they've experienced it, they've seen it, a question that you can now help them answer. And that actually makes your explanations and your teachings a lot stickier. They will remember those things a lot better. If your information, if your teaching is answering a question that they actually have. So you might look to see if you can collect the materials that will allow you to do an activity like that. So again, fairly simple materials, but I think kind of rich questions. What we might do now is sort of, I mentioned that if you had a vacuum pump, which perhaps some of the schools have, I don't think many will have them, but some of the schools may be fortunate enough to have a vacuum pump. So a vacuum pump is, literally just like a very effective version of those syringes. We'll change camera with that. So here is just a fairly thick-walled glass jar. And for the first kind of demonstration, into this, I can fit an entire jumbo marshmallow. Again, I will win. It will get in. All right, there we go. It's in. And just so we can see it properly, we might sort of put that back against a black surface. And I have here in my study, where we're working tonight, I have a vacuum pump, and I can turn that on and off with my foot. And so this is a rubber disc. It has a hole in there, which we can suck the air out through the hole. Now, all of the other activities I've done this evening, I'm pretty sure you will easily enough find the materials to go and do those activities. This one, I just thought we might do something just a little bit special, just so you can see it. So there's that marshmallow in the glass jar. You'll hear the vacuum pump cut in, a bit of a motor, and it'll start drawing air out. I won't let it run too long, but you'll see what happens. We can make that fill the glass jar. Each time we do it, and we let the air back in, the marshmallow ends up shrinking and getting smaller and smaller, because we're actually sucking the air out of the marshmallow when we're inflating it. Won't ever get quite so big again. It's now getting to be quite a hard, shriveled little marshmallow. And I did this for a workshop a little while ago, and one of the students asked, what would happen if you hopped out in space? So, and that was a great question, because they were thinking about where this stuff matters and what would happen to them. And so that's kind of where the marshmallow started. That's kind of where it is at the moment. It's a lot more solid, a lot tougher than this one. And so if you step out of a spacecraft without a suit into deep space is an almost perfect vacuum. So there is no pressure. So all of the gas that's in your lungs will expand, just as that marshmallow did. And so that made it very clear to the students about why things like pressurized spacesuits are important. But there was another reason that, or there's another consequence. There's another consequence of stepping out of a spacecraft into the cold vacuum of space. Here is a bit of water. I was just bringing it to the boil, but it's not actually boiling. Not at the moment. It'll be warm. Be quite warm. Now, digital thermometer is saying it's about 57, 58, 60 degrees. So the water in here is about 60 degrees. And we know that the boiling point of water is 100 degrees. But we also know that the boiling point of water is 100 degrees at standard pressure. So if we lower the pressure, we can demonstrate what happens to the liquids in your body if you step out of a spacecraft. You can see them starting to boil. So it's not getting hotter, but it is boiling under the reduced pressure. And that's a great demonstration, because we often talk about, but don't show, kind of this relationship, this change of state, which is a key concept in a lot of our schools and science teaching, that there is a balance between the gases above the liquid, the energy in the liquid, and the higher the pressure, the greater the energy needs to be to move a molecule from a liquid into the gas. And we can see that with that demonstration. We can, if we're careful, even if you don't have a vacuum pump, like I'm fortunate enough to have, if you've got a syringe, I don't know if you'll be able to see it. If you try this yourself, you will definitely see it. But if you take a syringe with water at about 50, 60 degrees, so it's not going to burn anyone. It's hot, but it's not going to burn anyone. If you can hold that closed and pull, problem with this, I'll change cameras so we can perhaps see what's going on. That might be better. Get a bit of light. There we go. Alrighty, that's where the camera is. So when I pull back on the plunger, you should see the water inside that will start to boil. So even if you don't have a vacuum pump, you can do that as a demonstration or get the students to try it themselves. So again, some of these things can be done as a demonstration where you're probably more familiar doing demonstrations and explaining things, giving answers, so describing what's going on, and the students will be interested in and seeing what's happening. But I really encourage you to think that for some of the time, run that sequence the other way around. Show them something interesting and ask them to think about it. Even if you haven't told them the science, if you haven't gone through that yet, there is some very good learning that we have, some very good research that not only that we do here in Australia, but internationally. If you can get someone curious, puzzled, wrestling with an idea, if you can get someone curious, they are much more likely to remember things which they see and things which they are told afterwards. And in fact, that's true even if the thing they're curious about is different. So if I just get you curious about anything first thing in the morning, they're going to actually remember more of the other stuff that comes afterwards, even if it's unrelated. So curiosity is a very powerful amplifier of how we run an active brain. So just being a curious person helps you be retentive, helps you remember things. So yeah, sometimes think about running that in the reverse order. I think we've got time, if I'm quick, to perhaps show you two final activities. One of which I in fact have learnt and adapted from some of the great teachers in India, the great practitioners of making wonderful demonstrations. And India has some people to be proud of, many people to be proud of, that do this sort of activity. So let me just set one of these up. All right. So as I said, this is sort of a version, slightly different geometry to one which I've seen done by some colleagues, friends of mine in India. 2 drink bottles and one glued on the side of this one to act as a funnel. I haven't put any liquid in this just yet, just so you can see what is involved and that there isn't anything particularly tricky. What we have, sorry, I'll adjust the camera. It's just in a bit close. My apologies. So we have a funnel on the top, just made from part of a bottle, glued to the side, 2 of the drink bottles. I have 1 straw that goes through the bottle lid into the bottom of the top bottle. I have 1 straw that goes from the bottom of this funnel down to the bottom of the bottom funnel. And I have 1 straw that goes from the top of the bottom funnel to the top of the top bottle. And what I'm going to do now, so I'll look around quickly, is I'm going to put some water in, make sure that lid is on tight. I'm going to put some water in to this second bottle. And if I think carefully, I have a funnel, so I don't make so much of a mess. All right, so I've just got blue water in it so we can see a little bit about what's happening. Always make a little bit of a mess. That's all right. I'll put the lid on. All right. Okay. There we go. And now we can see that the water is pretty much, well, the liquid in there is just staying put. Nothing particular is happening. It's all static. And one of the questions which I would ask at this stage is, when we think about pressure and liquids is, can water run uphill? Do rivers run uphill? If you want water to go up, what do you have to do? You have to pump it. You have to apply some force. So we're going to see whether or not we can get a fountain to actually run water uphill. All right. So we see now that I've added a little bit of water at the top, but it just keeps going and going. Have we created perpetual motion? Have we broken some of the laws of science? Can you understand why that's working? Can you understand why that's happening? That will just run and keep running. And the truth is that won't run forever, but it will run for a long time. And I think one of the interesting things is, because you've seen all of the working parts, and your students, if you built or you got them to build something similar, they would also be able to see all of the elements that are involved. And for me, the interesting and the powerful learning would be, once we've got them curious, is to come back and then talk to them to see if they can explain how it works, but without necessarily giving them the answers yourself. As I said, I'm always very keen to try and get the students to think into it, because it's those thinking skills that we really want to see the students developing. And whilst most of our teaching time is spent giving them facts, giving them answers, helping them to understand, it really is very important to allow some time in their teaching, even a small amount, to give them some problems to think into. Ones which are kind of interesting, but perhaps not necessarily all that important as far as, say, the formal examinations are concerned. So we wouldn't jeopardize their exam results, but it's still very good to give them at least some chance to strengthen and to practice their problem solving. All right, we're at kind of the end of the formal period for the workshop. I'm not sure whether or not anyone has captured any of the questions from the teachers participating, but I would certainly like to share with you kind of the great honor that I have for having been brought back to work with the team at the Science Centre and with the educators there in India. So hopefully from amongst those various activities, you will have had a chance to perhaps see some new activities that you haven't done before, see some things you might do as a demonstration, but I do very much hope that you will also have seen some activities that you might pose as problems to stimulate some thinking and some questioning, and even maybe just a bit of struggle sometimes amongst the students to explain what it is which they're seeing. So with that, I'd like to thank you all for your sort of attendance today. Thank the Science Centre and the ministries for helping organise these activities. And again, to thank the team there at the Consulate General there in Calcutta for bringing the support to allow this to happen together. So thank you all very much. Stay safe. And tomorrow we'll come back and we'll see how questions and chemistry fit together. So thank you all.
Yeah, thank you, Dr. Stuart. I'm from RSC Bhubaneswar. Now, we may allow at least some of our participants to interact for at least 1 to 2 minutes. Let us see who asks the questions to.
Sushant Raut.